All right, well, good morning, everybody. So last time we started talking about functional groups, and before we get into the material that I want to cover today, let's briefly review some of the things that hopefully you've started to memorize, and that is your functional groups. Give me some examples. Pardon? Hydroxy. So if we have a carbon connected to an OH, that's the hydroxy functional group. It's also known as what? It's an alcohol. What others? Thiol. Pardon? Carboxyl. We talked about carbonyl briefly, and it could be attached to a variety of things. We'll finish on that today. So carbonyl. What else? Pardon? Amine. Now we have three different kinds of amines. What kind of amine is that? It is a primary amine. Okay? One with a little degree sign. It is a primary amine. What makes it primary? It's only got one carbon-nitrogen bond, right? And so we can have, which would be secondary, and we can have, which would be tertiary. So we have primary, secondary, and tertiary amines. We can technically have 4 bonds to nitrogen, right, and to different carbons, but that's no longer an amine. Can you tell me why R4N, which would have a positive charge, a plus on the nitrogen, is not an amine? What do all of these amines have that I haven't explicitly drawn on nitrogen? Electron pair. An amine must have an electron pair, okay? Otherwise, it becomes what's known as a quaternary ammonium salt, okay? And so they do have different chemistries. What other functional groups did we learn about? Pardon? Ether. Yep. That seagull-looking thing, that's diethyl ether, right? So we have an oxygen that's connected to 2 R groups. What else? Yeah, and that's part of the carbonyl. We're going to talk about those today. So anything with a carbonyl, let's just avoid, because we didn't get to that on Friday. What else did we get to on Friday? Getting close to the end. Huh? Well, okay, so we had alkanes. Is that really a functional group?
No.
Why not? Can't really do much with it, right? Alkanes, pretty much all we can do is oxidize them and burn them, right? So they don't have much function. But when we take away some hydrogens, what happens? What do we get? We get alkenes and alkynes. The carbon-carbon double bond and the carbon-carbon triple bond are functional groups. We can do things with those really easily. What else did we cover? That's part of the carbonyls, and we'll get to those. We didn't actually cover those. What was X? Halogens, right? So fluorine, chlorine, bromine, and iodine, right? So yeah, alkyl halides also. And we learned the other day that these have varying levels of polarity, right? So alkyl halides are polar, carbonyl groups are polar, ethers have some polar bonds. But just because a molecule has polar bonds, does that mean that it is polar? No, right? We also have to take into account shape. So the example that we talked about was carbon tetrachloride, CCl4. Clearly has polar bonds, but the molecule itself is very apolar. It is not polar hardly at all. In fact, that molecule that we talked about on Friday used to be used in the dry cleaning industry. It used to be used to get your oils and stuff out of your wool suits and other things like that. Works really well. It dissolves grease because it's not polar, right? It's no longer used in the industry because it turns out to be a very potent carcinogen. And a lot of people that worked in the dry cleaning industry actually had high incidences of cancer. So we don't use it for that purpose anymore. In fact, for those of you who are going to medical school, it's one of the ways that they induce cancer into lab rats, is they actually lace their water and their food with carbon tetrachloride, and it goes off like a bomb in their kidneys, I believe, or their liver, and starts a whole cascade that leads to these little mice having cancer. So Yeah, we don't really want to clean our clothes with that anymore. So functional groups with the carbonyl. The carbonyl, as we talked about last time, is the carbon-oxygen double bond, right? That carbonyl is in itself a functional group, but it belongs to a variety of functional groups as well. It's what is attached to that C double bond O that distinguishes it from other things. So for example, if we have a carbon that's bound to a carbonyl and a hydrogen that's also bound to a carbonyl, we call these aldehydes, okay? So some carbon group, carbonyl, hydrogen, that's going to be an aldehyde. A ketone, carbon, carbonyl, carbon. We have a ketone, in this case acetone. This is your fingernail polish and paint thinner, okay? Fingernail polish remover and paint thinner is acetone. Carboxylic acids. Looks like we have two functional groups here. It looks like we have a carbonyl and an alcohol, doesn't it? Kind of looks that way, but in fact, this whole thing is the functional group. It has very different chemistry from alcohols, okay? And so there's an example of acetic acid. It's a carboxylic acid. Where do we find acetic acid? Vinegar, that's right. So if you like Italian dressings, that acidic taste that you have from it is due to the carboxylic acid, acetic acid. Esters, again, we have the carbonyl, but it also looks like we have a carbonyl and an ether, but in fact, this is one functional group. Can anybody tell me something about carboxylic acids in terms of their odor? They smell pleasant or unpleasant? They're unpleasant, right? In fact, butyric acid is really, really unpleasant. It's actually responsible for body odor. But esters actually have a very sweet smell, and usually flowers make esters. And one of the things that you're going to do this semester in lab is actually make a carboxylic ester, either this semester, maybe it's early next semester. But the difference between your starting acid and your product is night and day. You can tell that the reaction is going just because you go from a really stinky substance to something that smells actually quite pleasant. Amides, okay? We have a carbonyl attached to what looks like an amine, but again, it's one functional group, okay? Now, just like with amines, we can also have primary, secondary, and tertiary amides. Would you call this a primary amide, secondary amide, or tertiary amide? It is primary because it contains one and only one carbon-nitrogen bond, right? So what would a secondary amide have? It would have another bond to another carbon here of some sort, right? These bonds you've probably learned about, or these types of molecules you've learned about in biology as peptide bonds, proteins. That's what these are composed of, okay? Your proteins and peptides that are in your body right now are actually composed of secondary amide bonds for the most part. They're very strong, okay? For those of you who are in polymer science, there are materials that are polyamides. Can anybody think of a polyamide that is very famous? Can't think of one. Nylon. Nylon is a polyamide, okay? It's very strong. We use nylon ropes, right, like on boats and vessels and things like that because they hold up really well to the environment, okay? They're really tough. And then here's an example of what's known as an acid chloride. This is a special class of functional group simply because they're highly reactive. They're so reactive, in fact, that when you make them, you use them immediately. You typically don't store them for very long because they will react with the moisture in the air. If I came in here with a bottle of an acid chloride and I opened the bottle up, we have so much humidity here in southern Mississippi that it would react with the humidity and you'd see all this white smoke coming out of the bottle, okay? So they're very, very reactive. But nonetheless, all of these functional groups that we're talking about here all contain the carbonyl, okay? So once you've identified a carbonyl, you need to be able to identify what else is attached to it, okay? Are all of these molecules polar or nonpolar? They're very polar, that's right. They are certainly polar. Now, if you look at typical organic molecules that are useful, here's a couple of examples, okay? So here's an antihypertensive agent, atenolol, and here's an anti-HIV agent, Viracept. What you should notice right off the bat is there are multiple functional groups within each of those molecules, okay? And that's the cool thing about organic chemistry. We can take a molecule, put different functional groups in different locations and get different functions out of them, okay? So for example, if you look at this, you can clearly see we have an aromatic ring. That's the phenyl ring, right, that we talked about as being a functional group. We have an amide. What kind of amide is that? Primary, secondary, or tertiary? It's primary. We have an amine. What kind of amine do we have? That's a secondary. We have an alcohol. We have an ether. Taking all of these functional groups and placing them in exactly those locations give us a molecule that is antihypertensive. Now, if we look at this anti-HIV agent, it's a little more complicated, right? We have a lot more functional groups. Notice we have what looks like an alcohol. It's actually called a phenol because it's attached to an aromatic ring, and we'll learn more about that later. So it's a special kind of alcohol. We have an amide. What kind of amide is that? That's right. Here we have a sulfide. Sulfide looks like what other functional group? Looks like an ether, right? So sulfides and ethers are related because oxygen and sulfur are in the same family, right? And so what would we expect for the chemistry of a sulfide relative to an ether? Similar or unsimilar? And why would we expect them to be similar? Same family. We know that chemical properties tend to be the same in a family, right? Remember that families stand together, right? And so that's the way that we like to think about that, okay? So we have a sulfide here. We have another aromatic ring. We have an amine. What kind of amine is that? That's a tertiary amine, right? Lone pairs are there. We just don't show them. And then we have another secondary amide, okay? So again, taking these functional groups, placing them where we place them on a molecule gives us the properties that we're after, okay? So that finishes up what we should have gotten to last time. We had just a couple of slides that we didn't get to. And so today we're going to continue on into Chapter 2. And today we're going to continue talking about functional groups. Hopefully you're understanding that functional groups is a very, very important part of what we're going to be doing this entire semester, okay? So you need to be learning them, okay? We've already done a little bit of review, but we'll do a little bit more. We're going to talk about physical properties. Functional groups are responsible for the physical properties, and we're going to start talking about attractive forces and how functional groups, what role they play in the attractive forces. What do I mean by attractive forces? Intermolecular forces. We're going to talk about the different types of intermolecular forces. A lot of what we're talking about really harkens back to the things that you learned in general chemistry, right? So we just finished talking about carboxylic acids. Carboxylic acid, before I throw it up there, what is that functional group? What would it look like? Describe it for me. Okay, so a C double bond O or a carbonyl, which is how we would just typically, we would say a carbonyl with an OH attached to it, right? So, for example, formic acid. This is the simplest of the carboxylic acids. For those of us that go outside in our yard and mow the lawn and get bit by ants, we're very familiar with formic acid. It is the acid that is injected into you by fire ants when they're stinging you, quote unquote stinging you, okay? In fact, formic acid, you can look in the literature and you go back maybe 100 years, maybe a little longer than that. Chemists used to actually get formic acid by the distillation of ants. They would get big mounds of ants, they would put them in a flask, they would heat them up until they died and they pop open and the formic acid would distill out. You would not get much formic acid that way, but that is one of the original ways in which an organic chemist could acquire usable quantities of formic acid. Propanoic acid, a few more carbons. Benzoic acid has a phenyl ring. So what you need to understand is that this part is the functional group, but we can change what's attached to it, okay? And we can have different properties. Okay? Formic acid does have an odor. Propanoic acid certainly stinks. Benzoic acid is a solid. It doesn't have a very high vapor pressure. It really has no odor associated with it, okay? But I would imagine if you could boil it, get it into the gas phase, it would probably stink as well. Most of them do. Esters are also derivatives of carboxylic acids, okay? They have the carbonyl group, right? So we have situations that look like this. Amides, right? We just have the carbonyl attached to what looks like an amine, right? We have a primary, a secondary, and a tertiary amide, okay? So they have those general structures. Nitriles. We didn't quite get to nitriles on Friday. Can anybody from their reading tell me what a nitrile is? Where have you heard the term nitrile before? Have you heard the term nitrile? I bet you have. Gloves, nitrile gloves, exactly. That functional group is actually used to make a polymer, okay, that makes nice gloves that resist water and organic molecules pretty well, and it's fairly hypoallergenic, right? A lot of times in the past we would use latex gloves. We would give students latex gloves, but we don't do that anymore. Can anybody tell me what the problem with latex is? Now, there's a lot of people actually that have a severe allergic reaction to latex, and so we no longer hand out latex gloves to people. We give them nitrile gloves because they're hypoallergenic, okay? Now, the nitrile group is a C triple bond N, okay? These are organic derivatives of cyanide. You might remember cyanide from general chemistry. What do you remember about cyanide? Is it something you'd eat? No, why not? It's very poisonous, right? Hydrogen cyanide is a very toxic gas. It's actually what has been used to put inmates to death, okay? You don't want to be around cyanide. However, nitrile, we will give you gloves made of nitrile. You'll put it on, no problem. It's because the carbon of the cyanide is actually bound to another carbon. You don't have the negative charge associated with the cyanide, okay? So it can't bond to your hemoglobin. What's the hybridization of that carbon atom? And how do you know that? Well, that's why it's linear. But why is it SP? 2 bonds? It has 2 pi bonds, right? We have to be specific about the type of bond that we're talking about. One of these bonds is a sigma, and the other 2 are pi. How are those 2 pi bonds with respect to one another? What's the shape? If you were to build a model, how would those 2 pi bonds be? What would the angle between the 2 be? If I had a carbon with its p orbitals and I had a nitrogen with its p orbitals that are going to make the pi bond, what would the angle between those 2 pi bonds be? Would they be parallel? Remember when we drew out the orbital the atomic orbitals for carbon? We said 2px, 2py, 2pz. So where do those orbitals lie? Where does px and py lie on the Cartesian coordinates? On the x and the y-axis, right? So if we have those atomic orbitals that are forming these 2 pi orbitals, or pi bonds, I should say, what's going to be the bond angle between them? 90 degrees, right? So you will see one pi bond kind of in the plane of the board, if we were to draw it out, and one coming in and out of the plane of the board, or perpendicular to the plane of the board, 90 degrees to that, okay? So ethane nitrile, this is also known as acetonitrile. You don't need to worry about that, but it is a common solvent that is used in chemistry laboratories. Okay, it's dirt cheap these days. It's polar enough to do most of what you want to do. It dissolves a lot of organic molecules. If you end up working in any type of chemistry laboratory, at some point you will use the compound acetonitrile. But the technical term for it is ethane nitrile, and we'll learn more about nomenclature in another chapter. But just right now, we're kind of getting you exposed to the different names. Okay. Butane nitrile, 4 carbons. Notice we're counting the carbon that's part of the functional group in the numbering. Okay, because but is how many carbons? 4, right? So we've got 1, 2, 3, 4. Okay. Benzene carbonitrile. Cyanobenzene. Okay. Here we have, what functional group is this? That's the phenyl group, right? And then cyclohexane carbonitrile is just 6 carbons in a ring. Okay. Are these the same thing? Why are they not? The double bonds, right? And some of you mentioned on your note cards on Friday that you had a little bit of an issue with saturation and unsaturation. So this is a perfect example for us to discuss that. Just looking at the rings, how many units of unsaturation does an aromatic ring have, or this phenyl ring have? It has 4. And where are they? Okay, the double bonds in the ring, each one of them is a unit of unsaturation. And where's the 4th? The ring itself. So a unit of unsaturation is minus 2 hydrogens, if you will, right? So we know that 6 carbons should be able to handle how many hydrogens? What's the formula? Not minus, plus. 2n plus 2. So for 6 carbons, I should have 14 hydrogens, right, on an aromatic ring. But for a benzene ring, I don't. I only have 6, right? And so that tells me how many units of unsaturation I have. How many units of unsaturation do we have for a cyclohexane ring? 1. And where does that unit of unsaturation come from? The ring itself. And why is that an unsaturation? Okay, I have to remove 2 of those hydrogens, right, to connect the ends together. And so that is taking 2 hydrogens away from the hydrocarbon, right? And so that's exactly right. So good job. In your book, you have tables of important families of organic compounds, or the functional groups. I actually find tables like this to be problematic from my learning. You may learn very well from it, but I just have trouble keeping track of stuff in a table like this. I think for your functional groups, the best bet for you is to make flashcards. We talked about that on Friday. How many of you have started making your flashcards? Okay, a couple of you. You really need to know it. By the end of this chapter, which is Friday, you really need to be able to know your functional groups by name and by site.
So what should we put on them? Like the structural?
I would put an example, like we had in the previous table. You know, it gave an example of each one of the functional groups. I'd put that on one side of the flashcard, and on the other side I would list the name of the functional group. And I would go through them kind of at random, to where you're looking at a structure, trying to figure out what the name is, looking at the name and trying to figure out what the structure is. Okay? Again, this is the ABCs. You've got to have your ABCs before you can start writing words. Okay? And so the functional groups are really what we need to know as organic chemists moving forward. Okay? Those are the carbonyl-containing ones. We'll skip through that, since we just covered that again this morning. That first sentence says it all. I really can't overstate the importance of functional groups. Okay? Everybody that does well in this class knows their functional groups by heart. People who struggle typically struggle because they don't know their functional groups. And each and every one of you can know your functional groups. Okay? There's no barrier to knowing these things. Okay? And the reason that it can't be overstated is because of all these reasons. If you need to know how something is bound and the shape of the molecule, you're going to be looking at functional groups. If you need to know whether or not something's going to be a high boiling point or a low melting point or whatever the case may be, that has to do with intermolecular forces. That's going to deal with functional groups. Okay? If you need to know something about the physical properties, you need to know something about the functional groups. If you're trying to develop a material, right, that has a high melting point, that resists oxidation, that's going to, be a great material to build whatever with, you need to know physical properties, and to know physical properties, you've got to know functional groups. Also, in terms of nomenclature, how we name molecules is dependent on the functional group that they contain. And the chemical reactivity. How is this chemical going to react with this reagent? I can predict that knowing the functional groups. Okay? Because a functional group in a small molecule more or less behaves the same as that same functional group in a much larger molecule. Alcohols, pretty much so always react the same. There's some slight differences, okay? But if I see an alcohol, immediately in my mind, I know what I can do with that alcohol. I know that I can convert it into an alkene, for example. I know that I can make an ether out of it. And by the end of this semester, you'll know that you can do those things too. It'll just pop in your head, okay? I promise. But you've got to know your functional groups. So let's do a quick, take a minute, talk among your partners. Identify the functional groups in those two molecules. All right, let's start talking about penicillin G. Penicillin G, what is penicillin? It's an antibiotic, right? It's a very potent antibiotic. When I was a kid, it was the antibiotic you got no matter how sick you were. Today, not everybody gets penicillin anymore for a couple of reasons. But among those reasons is because a lot of people still consider this kind of the last line of defense that we have is penicillins. And we don't want bacteria to become resistant to it. And that was starting to happen. So we don't prescribe penicillin like we used to, okay? It is a very potent antibiotic, and it contains a variety of functional groups. When you looked at this molecule, what did you hone in on to try to identify the different functional groups? Started looking at the pi bonds. That was good. What else? Letters? Okay, so the heteroatoms, right? So things that weren't carbon and hydrogen. And so what you notice here is we have an aromatic ring or a phenyl group, right? And it's got the pi bonds in it. Here we have what kind of functional group? That's a secondary amide. That's right. Now some people pronounce that amide or amide. We pronounce it amide because amide actually means something a little different, okay? But it's spelled exactly the same, and it can be confusing. So we're going to call them amides, okay? What do we have here? That is a tertiary amide. That's right. It's also part of what's known as a beta-lactam. We'll learn about that later. It's the pharmacophore of this molecule. Does anybody know what that means? That wasn't in your reading. I'm just trying to see if you know anything about it. That's the pharmacologically relevant piece for this medicine, okay? All penicillins have this functional group, okay? That's what makes them a penicillin. They're beta-lactams, okay? And that's nothing more than a tertiary amide that happens to be cyclic, and we'll talk more about that later. What about here? What do we have? A sulfide, and here we have a carboxylic acid. You have to have all of these functional groups in this molecule for it to behave like penicillin. For it to work on the bacteria like it does, you've got to have the carboxylic acid. You've got to have the sulfide. You've got to have both the tertiary and the secondary amides. And you got to have them right where they're located. Otherwise, it doesn't work, okay? This is actually a fairly simple organic molecule, and let's talk about one that's even simpler. The one that you'll probably take after class at some point today, right? Ibuprofen. Why do we take ibuprofen? It's a painkiller. Cures our headaches, right? You leave class, you've got a headache, you might take some Motrin. What kinds of functional groups do we have here? We pretty much so have the aromatic ring, the phenyl ring, and a carboxylic acid. There's some alkane stuff out here, but by and large, the functional groups are considered to be the carboxylic acid and the aromatic ring, okay? One of the things that you're going to learn as we go through, I'm going to throw in a lot of medicinal examples at you throughout the whole 2 semesters of this course, because many of you want to go to medical school, and I want you to leave this class understanding that the organic chemistry wasn't there just to torture you for the MCAT, okay? It is very relevant, the organic chemistry that you learn, for your understanding of biochemistry, and it's very relevant for your understanding of pharmacology and how medicines interact with the human body and work. Both topics which you will need a lot of information about when you get to become a physician, okay? You got to know how this stuff works. Are you going to be synthesizing penicillin and ibuprofen? Of course not, okay? That's the chemist's job. But you need to understand the functional groups and the roles that they play in medicine if you're to understand at a molecular level really what's going on. And medicine has been going in this direction for a long time, and it's going to be continue to go in that direction of understanding things at the molecular level, okay? And so it's very important that you, again, have an understanding of these functional groups. I don't know why examples came up right off the top, but okay, here we go. Intermolecular forces have a major influence on the physical properties of compounds. Intermolecular forces are responsible for melting point, boiling point, for example, solubility, right? Can I take compound X and dissolve it in water? Maybe or maybe not. The functional groups will tell us, okay? Give me some examples of intermolecular forces that you all remember from general chemistry. Hydrogen bonding, van der Waals interactions, ionic bonds, dipole-dipole interactions. London dispersion is another name for what? For van der Waals, that's right. And I take either one of them. As far as I'm concerned, it's interchangeable, okay? So yeah, so how these molecules interact with each other, okay, over short distances, okay, are these intermolecular forces that we are talking about. Hydrogen bonding is actually a special case that is really nothing more than a dipole-dipole interaction, but it's a fairly strong dipole-dipole interaction, okay, and so we give it its own name as hydrogen bonding, okay? So, for example, you all learned about ion-ion interactions. These are salts, right? Sodium chloride is held together as a solid because of ion-ion interactions. Are those strong or are those weak? They're relatively strong, right? They're actually quite strong. How do we know they're strong? What experience do we have that allows us to know that these are fairly strong forces? Ionic. Ion-ion. They form solids. Very good. What else? Think about your everyday experience. High melting point. And we know that because if we take salt, which we cook with, right, and we throw it in a very hot pan, does the salt just melt? Never does it? However, if you have a hot pan and you throw butter in there, what happens to it? So there must be some difference between the 2 types of intermolecular forces there, right? The salt doesn't melt. Actually, you can melt salt, but not at home. Your stove doesn't get hot enough. If you've ever looked at molten salt, it's actually kind of a scary substance because you know what temperature that melts at, and you're like, wow, okay, this liquid salt. But nonetheless, these different intermolecular forces are responsible. You all talked about this intermolecular force an awful lot in general chemistry. It turns out that this intermolecular force is not particularly relevant in organic chemistry. And why is that? Okay, we need metals and nonmetals, right? And typically in organic chemistry, we're talking about things in this region, nonmetals, carbon, hydrogen, nitrogen, right? That's not to say that we won't have some ion-ion interactions that we talk about. But most of what we deal with in organic chemistry is covalently bound. And so we're going to be dealing with the other intermolecular forces, and largely we don't have to worry too much about these ion-ion interactions, okay? The ones that are really important for us are van der Waals or London dispersion, same thing. These are weak forces. Dipole-dipole interactions, these are fairly moderate. And hydrogen bonding, again, which is really a dipole-dipole, but it's stronger, okay? And so we put it out as its own class and we call it strong. So because van der Waals forces are weak, we can just ignore them, right? Absolutely not. Absolutely not. And in fact, we depend on van der Waals forces more than you know. So if you've ever gone home and you've had a big bowl of something that you want to put in the refrigerator and you put saran wrap over it to keep it all in the bowl and to put it in the refrigerator, what holds that saran wrap to the bowl?
Plastic touching plastic.
It's van der Waals interactions. If you've ever ripped off a big sheet of plastic wrap and it starts to fold in on itself and you sit there and you struggle trying to get it to open up, that's a weak force playing with you. Okay? It's weak, but when you have billions of them, a billion times a small number is still a large number, right? Will everybody agree with that? Billions or even trillions. So yeah, it's weak, but when you all of a sudden have that many different interactions going on, it can add up. Dipole-dipole interactions are moderate, and of course hydrogen bonding is stronger. What are the rules for hydrogen bonding? Anybody remember? Can just anything hydrogen bond? Yeah, so for our purposes, you have to have a hydrogen that's attached to either nitrogen, oxygen, or fluorine. Okay? Now if you continue on in your chemistry studies and you get into Dr. Wallace's upper level class, he will dispute that claim. And there are weak hydrogen bonds to other elements. But for the purposes of this class, we're going to be dealing with nitrogen, oxygen, and fluorine. Okay? Van der Waals forces occur because of temporary dipoles that are created in a molecule. Okay? So if you take the molecule methane, for example, CH4, it's tetrahedrally shaped, right? Is it polar or nonpolar? CH4? It's relatively nonpolar, right? It's essentially nonpolar. However, for it to truly be nonpolar, that would mean that the electrons never move at all. But every now and then, the electrons will find themselves a little more on the left or the right-hand side of that molecule, momentarily. And in doing so, it creates a temporary dipole, where one side of the methane takes on a slight positive charge, and the other side takes on a slight negative charge. That's what the delta means. It means partial. Okay? And so when we have a situation like this, we've got a small temporary dipole. What does that dipole do to its neighbor? It induces another dipole. And so what happens? Now you have positives and negatives, and what happens to those? Are they attractive or repulsive? They are attractive, right? And so they attract one another and they actually interact. Okay? Not a big effect for methane. Methane's pretty small. But now imagine taking a big sheet of saran wrap that has a lot of surface area and you fold it over on itself, right? And then you try to unfold it. It gets messy because it's holding on to itself because of all these van der Waals interactions. And it's holding itself together because of random acts of electrons moving. Okay? You're depending on your saran wrap holding your soup or whatever in that bowl due to random motion of electrons in a molecule, creating these temporary dipoles that only last fractions of a second. Okay? I don't really know the time frame, but it's quick. Okay? Holds on pretty good. So, van der Waals forces, the larger the molecule, the more surface area it has, it's going to play a larger and larger role. Okay? So, for example, if you look at pentane, 5 carbons, it looks something like this. And if you look at neopentane, it looks like this. Okay? Now, neopentane and pentane are what with respect to each other? They are isomers. They are constitutional isomers. They have the same number of carbon atoms, the same number of hydrogen atoms, but I think you will agree that they look quite different, right? Which one of these would you predict would have the higher boiling point, neopentane or pentane? Which one has the largest surface area? Pentane. Pentane has a slightly higher boiling point than neopentane. Even though it's the same number of carbons, the same number of hydrogens, it has exactly the same molecular weight, But pentane will boil slightly higher than neopentane because the surface area and the van der Waals forces are larger. Okay? And so we can use these intermolecular forces to predict the order of these physical properties. Okay, this looks more like a ball. Okay, it's not exactly a ball, but it kind of looks like a ball. And this looks more like a sheet. And if I take two balls and I try to put them together, do they interact with each other on a lot of surface? No. But if I take two sheets of paper and I overlay them, is there a lot of interaction? You bet, right? So it's all about these temporary dipoles. Large surface area means you've got more of them that can interact. Smaller surface area, less interaction, and that has an effect on the physical properties. Okay. If your atoms are polarizable, you will also have an effect. What does it mean to be polarizable? What's it saying up here? What's this really mean? What does it mean to be polarizable? I think I'm going to leave that one as a homework assignment for you all to come back Wednesday. Tell me something about polarizability on Wednesday when we come into class. So do some looking up on that one. Take-home message here is small atoms are not very polarizable. Larger atoms are more polarizable. You're going to figure out why that is through your homework, okay? But the larger the atoms, the more polarizable. The more polarizable, the more van der Waals interactions. The more van der Waals interactions, differences that you have in physical properties. What's the physical state of fluorine at room temperature, F2? Is it a solid, a liquid, or a gas? It's a gas. How about I2? It is a solid. Iodine is a solid. It sublimes very easily. Okay, and that is, it goes into the gas phase quite easily, but it is a solid. Okay, and it has to be a solid, or it is a solid, doesn't have to be. It is a solid because of this polarizability, and you have more van der Waals forces. Okay? Dipole-dipole interactions. For something to have dipole-dipole interactions, you must have polar bonds. The molecule must be polar. Here's an example. Acetone. Acetone has a dipole that is shown by this arrow in this direction. Does that make sense?
Yes.
Why?
Because the oxygen is more electronegative.
Right. The oxygen is the more electronegative atom. The carbon is more electropositive. The oxygen is pulling electrons in that bond closer to itself than to carbon, and we generate a dipole. That dipole will have a positive end and it will have a negative end, and it is permanent. It's there all the time. It varies in magnitude depending on how the bond vibrates, and we'll talk about that on Wednesday as we talk about infrared spectroscopy, okay? But nonetheless, the dipole is there all the time. And so acetone interacts with other acetone molecules by their dipoles lining up, just like opposite ends of a magnet will interact with each other, okay? You can think of it that way. And you'll learn more about that in your physics class. But dipole-dipole interactions. These are moderate, whereas van der Waals are weak. Why? Why are these moderate? They are permanent. That is exactly right. Van der Waals depends on this temporary dipole that only lasts a short while. However, dipole-dipole interactions depend on this permanent dipole that are there all the time. Okay? And then, of course, hydrogen bonding. Again, we're going to focus on oxygen, nitrogen, and fluorine. Here's an example of a hydrogen bond between two water molecules. What's the molecular weight of water?
18.
It is 18 grams per mole. What is the molecular weight of methane, CH4?
16.
It is 16. Do they differ by a lot? No. What is the physical state of methane at room temperature? It is a gas. If you went by the molecular weight of water, you would predict that at room temperature, water should be a gas. But in fact, water has a boiling point of 100 degrees Celsius, which allows water on Earth to remain liquid over a wide range of temperatures that we experience on Earth. That little tiny bond is responsible for life as we know it. It's strong. It allows water to remain liquid. We have not yet found life, as far as I know, that works on gaseous water. Liquid water is so important, okay? So we're going to pick up with this on Wednesday. We'll finish this set of slides before we get into the IR stuff. You all need to go over to the library. I have a book on reserve, and there's some reading assignments in there for infrared spectroscopy. You need to be aware of those terms. So go get a copy of it, read that material. On your note card that you have, please place your name on the front, and then on the back, tell me what method you're going to use to, do you not have a card?
We don't,
What method you're going to use to memorize your functional groups. Does everybody else have a card?